First, I thank Brian Gorgel for organizing this event, as well as giving me an opportunity to come and talk here. I'll use mine. So we had a nice hydrogen 101 focusing on production, storage, and transportation. My talk is going to be mostly focused on how can we efficiently use it. So that is fuel cells. So you see a diagram here. I don't see anything coming. I don't know. What's the problem? Is there another pointer? Okay, maybe so small. Anyway, hydrogen can be used in a fuel cell more efficiently. You have a negative electrode that is called anode. Then you have a positive electrode that is called cathode. And then in between you have an electrolyte. So the simple fuel cell is hydrogen on the negative electrode side, then you have air that can supply oxygen. So at the negative electrode side, you will have hydrogen getting oxidized to give you protons and then electrons. And that will come, electron will come through the external circuit. The proton will go through the electrolyte to the cathode. Then the electron and the proton combine with the oxygen, where the oxygen is reduced from oxygen molecule to oxide ions to produce water. So the product is only water if you use hydrogen. So it's a clean energy production. You can use the free energy change for this reaction, and then you can use this equation, number of electrons involved, the Faraday constant, and from that you can get the voltage. So theoretical voltage is 1.23 volt. If there is no loss, nothing else is happening. You can also compute the efficiency. If you do that, theoretically 83%, but largely there will be some of the energy will be released out as heat. So generally you will get anywhere from 50 to 60%. And sometimes you can use that heat to heat the building or to get hot water. Then you can have efficiencies, combined efficiencies, maybe 60 to 70%. So it's a lot better than using conventional fuels. So that's why a lot of interest. There are a lot of fuel cells. It's not new. It's known for a long time. The phosphoric acid fuel cell, I'm also giving you the temperature, operating temperature here. Phosphoric acid fuel cell is known for a long time. NASA used to work on it in the 60s, 70s. So basically same kind of reaction. Here it gives the anode reaction. There you get the cathode reaction. And I also give you the operating temperature. Now, phosphoric acid is liquid, that's not good, leakage and other problem, corrosive. So largely these days it's focused to replace phosphoric acid with a solid electrolyte membrane, and that is Nafion. That's a commercial name. Sorry. This one, I'll come back to that later. That is the formula. A fluoropolymer with a sulfonic acid group, the proton from here can be transported. So that is called proton exchange membrane fuel cell. Instead of hydrogen, with the same kind of setup, if you use methanol or ethanol, then you will have direct methanol fuel cell or direct ethanol fuel cell. But when you have hydrogen, it is hydrogen, one bond hydrogen, easier to break it to get H plus ions. When you have methanol, it is a 6 electron change. It's complicated, very sluggish. If you go to ethanol, then it is a 12 electron change. So that is even more complicated. If you go to propanol or butanol, it will be even complicated. So that's all. These are all similar, excepting changing fuel here. Alkaline fuel cell means you can use KOH instead of phosphoric acid, or similar to this, instead of a proton transporting membrane, you can use a OH transporting membrane, and that is hard. H plus is easier to transport, whereas OH minus is difficult to transport. And these days, a lot of work has been happening in developing OH minus conducting membranes, and a lot of progress, but it's not quite there yet like hydrogen conducting membranes. So temperature is given here. You will see proton exchange membrane fuel cell 90 degrees because it has to be operated less than 100 degrees C. The reason is Nafion needs water to transport proton, that is called vehicle mechanism. So the proton is conducted as you have water H2O that captures a proton. It will be transporting as H3O plus. So water is the one carrying the proton moving, that is called vehicle mechanism. When you go to methanol, it can evaporate. In principle, you could use at 90 degrees C, but you will have evaporation as well as methanol will cross over through the membrane to the cathode. That is a big mess, so you can't use it at higher temperature. Of course, if you use at higher temperature, you will have better kinetics, but unfortunately, because of the methanol crossover to the other side, as well as things getting evaporated, you have to operate around 60 degrees. Molten carbonate fuel cell, you use molten carbonate as the electrolyte, operating temperature 600 degrees C. So, it's not easy. You have a molten carbonates, but that's another one. The third one, the last one is solid oxide fuel cell, where you don't use a proton conducting membrane. You use a oxide ion conducting membrane, so that is an oxide ceramic. This can operate from 500 to say 900 degrees C, depending upon which oxide ion conducting membrane you use. I will talk about a little bit about that. The advantage here is you don't need platinum. You can use non-platinum catalyst. Also, you do not have to produce hydrogen separately. We have methane, natural gas, you can directly feed into it because higher operating temperature. So, platinum is out. You do not have to produce hydrogen somewhere and transport. You could directly use methane here. The advantage here is efficiency is higher, as I pointed out earlier, compared to conventional way of using. Now, this is the bulk of my talk to tell you what are all the challenges. So first, we know what we need to do, but the commercialization is hampered because of cost. Main problem is cost, durability, as well as operability problems or operability challenges, I call. Because you have to control the temperature, you have to control the water, your membrane need not be flooded, your temperature cannot go above 100 or below, fuel cell emits heat, so controlling temperature, maintaining heat and maintaining water in the fuel cell is system issue that should be done properly. So I take 3 fuel cells here, proton engaged membrane fuel cell and direct methanol fuel cell, they are similar. And then I talk about the problems with the membrane separately, the catalyst separately, then I separately talk about solid oxide fuel cell. So first with the membrane, as I showed you, it's a fluoropolymer. Nafion had the patent long back. Anytime you deal with the fluorine, the processing cost will be high. Fluorine is very reactive, that's why the membrane is very expensive. But it works great, long backbone. And then this is sulfonic acid group with fluorine here. That is why fluorinated group here, that's why you got good conductivity. Now that membrane conduct proton using water as a vehicle. Therefore, if you go above 100 degrees C, water, it will become dry, it cannot work. So limited operating temperature. And it also needs to be wet, so humidification system. You have a fuel cell, then you have a humidification system. So it's getting complicated to have the temperature less than 100 degrees C, complex humidification system. If you have methanol fuel cell, that membrane will allow crossover of methanol from the fuel side to the oxygen electrode side. Then it will mess up the cathode electrode, lot of problem, mixed potential, efficiency going down, all those issues. It's a fluoropolymer. So when you reduce oxygen, it is supposed to take 4 electrons. O2 molecule should go to O2 minus. Instead of that, it may take 1 electron to form superoxide, O2 minus, or 2 electrons to make peroxide, O2 2 minus. Superoxide and peroxide are very reactive. They will corrode. So that will cause fluorine release from the membrane. If it is, then it will be degraded. Catalyst, we all know, platinum abundance is limited, expensive. And then the other problem is platinum poisoning. So if you have here, this tells you the coverage of carbon monoxide and hydrogen on platinum surface. This is degrees Kelvin. So if you are at room temperature, then your platinum surface is covered predominantly by the carbon monoxide, trace amounts of carbon monoxide, parts per million levels of carbon monoxide you may have in your fuel if you are producing from hydrocarbons. So cleanup is very much necessary. Otherwise, platinum surface will be covered by carbon monoxide. It does not have access to the hydrogen fuel. If you go to high enough temperatures, say for example, above 150 degrees C, then the coverage of platinum surface by hydrogen is more, by carbon monoxide is going down. So ideally, life will be easier. I do not have to spend a lot of money to clean up the hydrogen fuel, to get rid of carbon monoxide, even trace amounts, if I can operate my fuel cell at 150 degrees C or 200 degrees C. Unfortunately, the membrane we have now cannot work above 100 degrees C. So the challenge for research, can we develop a dry membrane that can operate around 150 to 200 degrees C with acceptable proton conductivity? And nobody has it. Nobody has it which can be used for commercial application. Okay? Then, when you have the fuel cell electrode, if I put all platinum, I will go broke. So generally in the electrode, cathode or anode electrode, 80% is conductive carbon. Only 20% is platinum. So the cathode is 20% platinum, 80% carbon. Then when you operate, carbon can undergo corrosion, and when you make this electrode with 80% carbon and 20% platinum, it will be nicer if I can have access to each platinum particle sitting there. Unfortunately, when you make the slurry and then do that, some of the lot of platinum may not be accessible. So utilization goes down. So how do we engineer the electrode fabrication so that I have good access to all the platinum particles? Any amount, any little thing I can save with platinum is good because it's very expensive, prohibitively high cost. So then carbon will also undergo corrosion with your peroxide, superoxide produced, so that's another challenge. Now, you see here we calculated the theoretical voltage 1.23 volt. It is supposed to be. But oxygen, you have O2 molecule. One oxygen bonded, there are two bonds, then another oxygen. So I have to bring a big hammer to hit it hard to break it into two oxygen and oxide ions. So that process gives to lot of loss here. So all the loss is happening because of the sluggish, very poor kinetics to reduce oxygen molecule to oxide ion. You have lost this green color here, thick green. You have lost a lot of voltage. And then hydrogen oxidation, yellow one, not very much problematic. Hydrogen, one bond, hydrogen, you say, it's broken, right? It's like that, easy. Platinum can do that easily. This is the platinum, the best catalyst we know. Then you can have cell resistance, electrolyte resistance, or your current collector resistance, all those, that's the ohmic drop. So that's not a big problem. You can design it well. If you are trying to draw current too much, that mass transport problem will come, meaning you are trying to draw too much power, then can you have quick access to hydrogen, at the same time quick removal of water? Quick access to oxygen, quick removal of water. All those needs to happen. So that is mass transport. Pathetically, under normal, reasonable operating conditions, the voltage goes from 1.23 expected to approximately 0.6 or 0.7. Too much loss. catalyst problem. So what can I do? Can I invent another catalyst which will be stable and better than platinum? I don't know. So there are a lot of fundamental research happening, not just today because of a lot of interest in hydrogen, 50 years, 60 years, 100 years. This is from Professor Bart's group in chemistry department some years back. The idea here is, can we replace platinum with something else? The idea here is, you think of the process, the catalyst has to first absorb or form, have some kind of attraction to oxygen. So that means the free energy of oxide formation has to be negative. So if you take some of these, like vanadium or lot of metals, vanadium, titanium, molybdenum, tungsten, they're all very fond of forming oxides. So they have very negative free energy. So they can very easily absorb oxygen and then get bonded. If you take another metal like silver, gold or platinum or palladium, they have positive, high reduction potential, therefore they will do the second reaction. So the idea here is, okay, instead of only taking platinum or only taking palladium or silver or gold, can I make an alloy in which I will have one of this element and one of this element here. If we make that alloy, then you can have both reactions going. So that's the idea. With that, we did some experimental work in my group, having particularly palladium and cobalt, or palladium and molybdenum, or few things. So the black curve here is the commercial platinum. These are some of the palladium-based catalysts. Palladium is a little bit cheaper than platinum, but not as expensive as platinum. So there are also now catalysts generally, instead of using platinum, they use PtCO, one platinum, one cobalt, or PT3CO. They are actually better than the pure platinum. That is because of this kind of concept. Cobalt helps to do the first reaction, the platinum helps to do the second reaction. So this is just an idea to give you. There are a lot of ways one can think of. Membrane, can we make membrane which can operate at more than 100 degrees C? So we had some ideas. These are all old. You see here, 2006. Supposing if I take an aromatic polymer like this, polyether ether ketone, if I sulfonate that, I will get sulfonated polyether ether ketone. That is something like nafion. Although nafion is an aliphatic polymer, flexible, it will form void channel, lot of methanol going or other things going. Here it is a little bit more rigid because it's aromatic polymer, so that's an acidic polymer. If you take another polymer, sulfone, polysulfone, and to that if you tether a nitrogen containing group, as you see here, heterocycle, then the idea here is, if you blend this is basic, that is acidic. If you combine this and blend it, the idea here is, there can be interaction between the sulfonic acid group, acidic group from this polymer and the basic group from that polymer. So can that allow proton conduction without water? Yes, it allows, but the proton conductivity is not sufficient. So we were not able to use in any meaningful way to get good current density with this kind of dry membrane. So we use that as a combined Groth's mechanism and vehicle mechanism. And these are very cheap, by the way. These polymers are very cheap. They are compatible with each other because they are same aromatic polymers. And high thermal mechanical properties, good thermal stability, all those good things are available, industrially available polymer, much cheaper than nafion. So we did some work by tethering lot of different things, as you see here, maybe not necessary for you. Finally, we found out it is better for methanol, direct methanol fuel cells. So I show you some data here. That is again commercial nafion membrane. We have a lot of catalysts here. So we have tethered lot of groups. What those acronyms are, they're all here. Only the tethered groups are different. The idea here is, if I have too many nitrogen groups, can they transport the Groth's mechanism better? That's the idea here. But little bit changes, some improvement, but not to the level to use them as dry membranes. So I will summarize here that particular membrane aspect. This is nafion. Nafion have 115, 117. As the number increases, the thickness of Nafion membrane is higher. That's all. You can see proton conductivity has higher proton conductivity. This peak I was talking about, that has lower proton conductivity. But if you make the blunt membranes, the proton conductivity is increasing. The other thing is methanol crossover. Nafion allows lot of methanol crossover, which is not good. Speak allows smaller amount of methanol crossover because it has narrower channel. If you tether these grooves, then the methanol crossover is less. So you have a competition. You should have reasonable proton conductivity and less methanol crossover. So something like this, for example, that is the best. Low crossover, reasonable conductivity, so that is better than anything else. So that is what you have here. So why does it have reasonable proton conductivity and less crossover? You can do small angle X-ray scattering. Brian is very familiar with this. If you do Nafion, that is the channel, this channel diameter. If you do speak, that is smaller. This is inverse, so right side means it is smaller. As soon as you have this blunt membrane, when you tether, that's moving to the left. That means the channels are opened a little bit. Why are they opened? A little bit more. There is acid-base interaction between the basic group and the acidic group from this speak membrane, acidic polymer, and the basic polymer. They want to interact, they get inserted into the channel. That's why it is getting a little bit open. So it's good science. Now I pass on to solid oxide fuel cell. It's all going to be all ceramics here. Your membrane is not a polymer. Generally fluorite, the first one you see here, but it needs operating temperature more than 800 degrees C. Then you will have a lot of thermal degradation, corrosion. So there are other electrolytes. This is called GDC. It can be operated at 500 degrees C. If you go above 600 degrees C, then it will also conduct electron because cerium will get reduced to cerium 3+. This is another membrane, a perovskite structure that can operate at 600 to 800 degrees C. There is a big push to operate solid oxide fuel cells anywhere from around 600 degrees C, above 500 degrees C, instead of above 800 degrees C. Then your current collect or your interconnect, everything will be easier, thermal degradation will be less. That's why a lot of interest to do that. Now anode, the electrodes have to be ideally a mixed conductor, meaning the electrode should allow whatever the working ion is, if it is oxide or proton, they should allow to move. They should also allow electron to go through. In the case of proton exchange membrane fuel cell I talked about, you mix platinum with conductive carbon. And then you also add a little bit of Nafion. So Nafion does the proton conductivity in the electrodes. Carbon does the electronic conductivity in the electrode. That is not the best situation. Ideally, you want one material which will do both, which you have in the solid oxide fuel cell. For example, in the anode, still it is not good. You have these, they are mixed conductors, good, but their catalytic activity is not good. They are perovskite oxides. So what they use is the electrolyte, like Nafion, with conductive carbon. Here we use zirconium oxide, doped zirconium oxide with nickel. This gives electronic conductivity, that gives oxide ion conductivity. Ideally, these kind of things will be better, but catalytic activity is not high enough. These are really intrinsic good mixed conductors. They have good electronic conductivity, like metallic. They also have good oxide ion conductivity. But this catalytic activity is not high enough. You have to operate about 800 degrees C. This is the best. You can operate at 600, 700 degrees C. But cobalt undergoes low spin to high spin transition, huge thermal expansion. So your electrolyte thermal expansion is 12 or 13. This thermal expansion is 22. You go to high temperature, thermal expansion mismatch, delamination, leakage, explosion. You can't have that. And also interconnect. Another, you can't use wires because regular metallic wires, they can get oxidized. So interconnect is again a ceramic. So everything is ceramic here, nice. The main advantage is there is no platinum here. You could also, in principle, use methane as a fuel directly, natural gas or any other hydrocarbon fuel instead of hydrogen. Now, there's a lot of things here. The conductivity of that mixed conductor depends upon how much you dope. These materials, something called perovskite. It's also, now people are familiar with the perovskite because of the solar cell. There's a lot of, the bonds don't expand the same way. The AO bond has larger thermal expansion than the BO bond, so when you change the temperature, the bond expansion is different, so some geometric matching can change. The bond can become more straightened, so it will widen, the band width will widen, so you get better conductivity. So short, this is what you need. If you take simple lanthanum, cobalt oxide, it's a semiconductor. You see a temperature increases, conductivity increases, semiconductor. Beyond a certain amount of doping, these bonds become straightened, good overlap. The overlap integral goes up, bandwidth increases, they become like metallic as you see here. Temperature increases, conductivity decreases, that's metallic. And also it depends upon, you can choose a lot of different ions, where these ion redox energies are located with respect to the top of the oxygen 2p. You see cobalt already overlapping with the top of the oxygen 2p band, highly covalent mixing, electron can transfer very easily. That's why cobalts are the best catalyst for solid oxide fuel cell. By the way, cobalt is also the best cathode for lithium-ion batteries. That's why it is expensive. If you go to manganese, well above, so it has less conductivity, so you have to go to higher temperatures. So, now I talked about thermal expansion mismatch with the cobalt. Killer. So we know chemistry. So what we did was, the reason is, if the cobalt is in the 6-fold octahedral coordination, it goes same electronic configuration, same oxidation state. But if it is low spin, smaller size. If it goes to high spin, larger size. That's in addition to the normal thermal expansion. Going from low spin to high spin makes additional expansion. That's why you have thermal expansion 2 huge 22. So the idea in my group was, okay, let us work with tetrahedral site cobalt ions. They will not have this kind of transition. So we found some materials in which cobalt is in the tetrahedral, no low spin or high spin transition. So these materials have thermal expansion exactly similar to the membrane or the electrolyte we use. Great, but the catalytic activity is not as good as the other perovskite cobalt oxides. You see here, I don't know whether you are able to see or not, this is a regular cobalt-based perovskite. You can see cracks when you operate. This is the one we developed with this. There is no crack at all because thermal expansion mismatch is not there. It is ideally matching. So a lot of ways, chemistry, basic inorganic chemistry, organic chemistry for membranes, you can design and try to come up with materials which can make things better. By the way, these membranes I am talking about, they can also be used for gas separation. Our air gas, air liquid, all those use these kind of membranes. And then they can also be used to produce syngas from methane, natural gas. Syngas is carbon monoxide plus hydrogen. You can produce that. From that you can remove carbon monoxide, then you can use hydrogen as a fuel in the fuel cell. So these are very interesting kind of materials, lot of solid state chemistry associated with these oxides. They are intrinsic mixed conductors, normally very hard to find materials like that. The final one I want to show is, right now solid oxide fuel cell uses the electrolyte with the nickel metal mixed, that is the anode. When you have methane, you will produce carbon, coking, that is called coking. Or it may have sulfur fuel, sulfur impurity. If it is, nickel will form, carbon will deposit on nickel metal, sulfur can react with the nickel metal to give you nickel sulfide, so that is a problem. So the magic here is, with the same nickel, we add only 1% tungsten. By the way, molybdenum can also do this. 1% tungsten. When you do that, you produce water there, so tungsten goes to tungsten oxide when you have nickel tungsten alloy, and tungsten oxide can interact with the water to form something called hydrogen tungsten bronze. They call it as bronze because it's metallic. Sodium bronze, potassium bronze, hydrogen bronze is metallic. So that hydrogen, it captures hydrogen or proton from water to form this. That can also be written like this. You have OH group. So the catalyst captures water and supply this OH group to carbon. So carbon is oxidized to carbon dioxide. So it's like a recycling. Supplying hydroxide so that deposited carbon is oxidized to carbon dioxide and the catalyst is regenerated. So it's going in the loop. And then if you do that, this is without tungsten, this is with tungsten, the green one, you see a stable operation. So a lot of ways one can design materials. I think this is my last slide. I'll be happy. A lot of chemistry, but that is a basic starting point, right? If you want to change or overcome the problem, then you have to design newer, good materials, more efficient materials.
Well, thank you.
Questions?
Any questions?
Thank you, Ram. To say you know a lot about the material science would be an understatement. But for those of us who don't, how do you think about the deployment of existing technologies, giving all the flaws you've gone over, versus waiting for people like you in the lab to come up with a different solution? It's a broad, hard question, but how do we think about, for those who say, we need to move forward quickly versus come up with new technologies? What do you have any comments on that?
Yes, so basically what I talked about was the problems with the existing materials and how we can approach to have better materials. That's what I basically talked about.
Yeah, so I'm saying, given all the flaws that you know in existing technologies, how fast do you think we should deploy them now, given all the flaws that we know?
How fast we can...
platinum electrodes and all these kinds of things.
How fast you can deploy the fuel cells? Is that the question?
Well, should we install a bunch of existing technology, even though you know the flaws that it has, versus keep waiting for you to come up with a new, better materials?
The biggest problem is cost is prohibitively high. That's why the ideal technology for car is fuel cell, right? You do not have to worry about charging station, all those. You go same gas station, there is another cylinder, then you swap it, done, right? But it's expensive. That is the issue. Cost is a major issue. Cost comes from membrane, largely from platinum, right? So if you want to really have widespread commercialization, you have to reduce the platinum content way down than what we have now, or completely come up with another catalyst, which will be, there are catalysts which are active, good, but stability is a problem. You operate at 90 degrees C, you have all this corrosive environment, they generally tend to dissolve. Then they also migrate from one side to another side. Some metals or catalysts you use, they may form ions, they may go through the membrane because they are porous, so that's the problem. So cost is the biggest problem. So if you want to really quickly deploy, you have to quickly develop materials which can be lower cost. People know what to do, how to operate, but cost is very high. I don't know whether I answered your... I do not have a solution to deploy right away.
Well, can I ask it this way? What is the best technology right now for fuel cells? What's your top?
Nafion membrane, platinum catalyst, that is the best.
Which one?
Nafion membrane, the membrane I talked about fluoropolymer, and then platinum catalyst. If you want to commercially do it, that's what you have to do it now. Actually, it's not platinum, it is platinum cobalt alloys, PtCO or PT3CO. So that reduces the cobalt content. And also it is a little bit more active for the reasons I was talking about. One oxygen capturing metal, that's cobalt. One metal that will reduce oxygen easily.
Any other questions?
There was a lot of interest when second Bush, he was president, some of you know. Then it went away, all battery. Now it is coming back. I think resources are important. If they pump a lot of money, then it's a fishing, but not completely randomly fishing. There are a lot of brainy, educated people, so you use your intuition, you use maybe AI can be used as well, data mining, all those can be used. But resource is the most important one. Yes?
So thank you for your presentation. First, I have a question on the one of the things that you show that the platinum is covered by the carbon monoxide. In the proton exchange fuel cell, where does it come from, the CO?
Because you produce hydrogen. If you produce hydrogen by water, by the way, I didn't talk too much about electrolysis. Some of the catalysts I talked about, they can be, for electrolysis, this is another question, another thing I will do that, then I will come back to you. For electrolysis, the cost of catalyst is important. So some of the catalysts I talked about, they can also be used for electrolysis. For you, it depends upon how hydrogen is produced. If you produce hydrogen from water, clean, there is no problem. That's what you need. But if you produce from hydrocarbon fuels, then you will have carbon monoxide present there. That's where it comes. But largely it is produced from hydrocarbon fuels, right? So then how do you get it up? You have to really clean.
So I think we're out of time. Let's thank Dr. Manthiram.